Hello everyone, I hope you're doing well. In this MTH 141 video, we're taking a look at question 1.2.4 from the textbook A First Course in Linear Algebra by Kuttler. You can find my notes for this course on my website, tutor.ca, where you can also find information about my private tutoring services. Okay, so let's read the question. Do the three planes x plus y minus 3z equals 2, 2x plus y plus z equals 1, and 3x plus 2y minus 2z equals 0 have a common point of intersection? If so, find one, and if not, tell why there is no such point. Okay, so we have a system of three equations in three unknowns. So there's three equations here, each one has three different variables. So let's write that out as a system. So I'm gonna write my little system bracket. And we have here x plus y minus 3z equals 2 as our first equation. 2x plus y plus z equals 1. 3x plus 2y minus 2z equals 0 is our last equation. And we're looking at if this system has a unique solution. Well, actually, it doesn't actually have to have a unique solution, but any solution, right? Does it have a solution here that all these three planes pass through? Okay, so to solve this, we're going to have to use elementary row operations to figure this out. Before we do that, I think it might be good to graph this, just to give you a good idea, to give us an idea of if they really do have a solution. So let's go on GeoGebra. And let's graph these three planes quickly. So it's going to be x plus y minus 3z equals 2, 2x plus y plus z equals 1, 3x plus 2y minus 2z equals 0. And there's our three planes, right? And so do these three planes have a unique solution? Well, these two planes intersect on this line here, right? These two planes intersect on the line. And then we got to ask, does this third plane also intersect that line at any point? So we can't really tell from the graph. I mean, the graph, it's really good to give an idea of like what we're looking at. What do these three planes actually mean when we say, we have three planes and we're looking for a point of intersection, right? So we can't really get a definitive answer from this just yet. I mean, as nowhere on this graph do they intersect, but that doesn't mean that somewhere way over there they don't intersect. So for now, it looks like they might not. They might not have a common point of intersection, right? Because as you can see, right, this forms a nice, what I'm looking at is these two planes, they form a line where they intersect, right? That line right there in their intersection. That plane doesn't look like it crosses that line, this third plane. And so my idea is that, no, they're not going to have a common point of intersection. Okay, but after we looked at that, now let's do it algebraically and try to take a look at how we can find the solution. So what we're going to do is we're going to use our elementary row operations. Oops, let me find the elementary row operations. Here they are. And so using these elementary row operations, we're going to be able to reduce this system or transform it in a way that doesn't change the solution set. That's a very important thing that elementary operations don't do. They don't change the solution set, right? It's going to let us actually get numerical solutions here. As in like z values, y values, x values, well, x, y, z values that solve the system. So to begin, it's going to be a little bit of a long one because we have three equations, three unknowns. It's going to be a little tedious to do with elementary operations. That's what the whole next section's about, Gaussian elimination. How to do this in a much more systematic and a simple way. Elementary operations are very important to act as a foundation for linear algebra. And so understanding them is very important, but they're not super practical. Just like the definition of a limit is not super practical, right? But it is important to understand the definition of a limit, just like it's important to understand the elementary operations here. Okay. So let's start here with what our goal is. Our goal is to get one of these equations with only one variable. That will let us just read off one of the, or just simply solve for one of the variables, and then we can back substitute, which is like we know one of the values, substitute back in, and then we have a simpler system to deal with. So the easiest way to do that is to start with this top equation, leave that generally how it is. In fact, we're going to pretty much leave this equation exactly how it is. We're going to remove this x term. Remember, when I say remove, I mean make the coefficient 0 using these row operations, specifically using this row operation. Remove this x, okay? And then remove this y. What's going to end up happening when we do that is we're going to have, first of all, on the bottom, we're going to get our goal, which was that we'd have one equation, one unknown. We just have, z with some coefficient. Of course, the coefficient won't stay the same because we're doing a bunch of operations to it. And this value won't stay the same because we're doing a bunch of operations to it. But we will lose the x term and the y term, and we'll be able to just read off the z value. Substituting that back into here, look, we don't have an x term. We only have a y term and a z term, but now we know z from this equation. So we can actually just solve for y really simply as well. And then back up here, well, we know y, we know z, we can just solve for x. That process is called back substitution, and we're going to do that at the end of the video. But for now, let's get rid of these three terms right here. That's the main part of this exercise. So to begin, we got to remove this guy. So always a good place to start when you're doing questions like this is to say, well, I want to remove x. So I'm going to make all the coefficients on the x terms equal to 1. This step helps us deal with this whole process. It makes the step number 3 as simple as possible. And that's, I think, my goal is to make step number 3 as simple as possible by doing maybe one extra operation first. But that's okay, because step number 3 is usually a little bit of a tricky one to understand. So let's look at our x terms. I have a 1 here, I have a 2 here, and a 3 here. So I'm going to change those 2's and 3's into 1's. So to change this 2 into a 1, well, I have to multiply by a half. So I'm going to take row 2 and multiply that by a half. That's a type 2 elementary operation. I can multiply any equation by a non-zero number. Rows and equations can kind of be used the word row and equation can be used kind of interchangeably here. Okay, so let's look at that. We're going to do row 2 times a half. And you know what? I'll just write that here now. So row 1 didn't change. X plus y minus 3z equals 2. Row 2 is just going to be multiplied by a half. So 2 times a half is 1. 1 times a half is 1 half. 1 times a half is 1 half. And finally, 1 times a half is 1 half. And our third equation also didn't change. 3x plus 2y minus 2z equals 0. And these three equations form our new system. Okay, now I'm going to do row 3 times a third, right? Because that's going to get rid of that coefficient on the x term there. So generally you multiply by 1 over whatever's on the x term, whatever number you want to get rid of. So our new system, well, equations 1 and 2 aren't changing. So x plus y minus 3z equals 2 isn't changing. X plus a half y plus a half z equals a half isn't changing. And now multiply the last equation by a third. So 3 times a third is 1, so it's just going to be x plus 2 times the third is 2/3. Minus 2 times the third is minus 2/3. And 0 times the third is 0. And these three equations also form a system. Okay, so now we've gotten our x terms and how we want them. So I'm going to start by removing this x term, and then I'm going to remove this x term. To do that, I want to replace row 2 with something, right? So I'm going to take row 2, replace it with, remember I'm allowed to do that because of this type 3. Replace any equation with itself added to a multiple of another equation. So I'm allowed to take row 2, replace it with itself added to a multiple of another equation. And there you have it. So this is going to get rid of that x, because look, what's going to happen is that we're going to take row 2, x, which contains an x, and subtract negative 1 times r1, same thing as minus r1, right? And subtract off x. X minus x is 0x. So you see that's what's going to happen here. So our first equation stays the same. X plus y minus 3z equals 2. Our second equation is what's changing. Row 2 minus row 1. X minus x is 0x. 1 half minus 1 is negative a half y. 1 half minus negative 3 is a half plus 3. Be very careful there. A half minus negative 3 is a half plus 3. So a half plus 3, well, I'm just going to write that here. I'm going to say plus 1 half z plus 3z equals, and I'll deal with what that is in just 1 second. And then row 2 minus row 1 is still 1 half minus 2. So 1 half minus 2. And then finally our third equation, row 3, isn't changing. It's just x plus 2/3 y minus 2/3 z equals 0. Okay, and let's deal with these fractions here in the middle. What are these fractions? So 1 half plus 3, well, 3 is the same thing as 6 halves, right? 6 halves. So 1/2 plus 6/2 is 7/2. So it's going to be plus 7/2 z. And now 1/2 minus 2, well, 2 is the same thing as 4 over 2. 1 minus 4 is negative 3, so negative 3/2. And the very important thing that happened here is that there's a 0x there. So that x term has gone away. Now to get rid of this x term, we're going to do a very similar operation. We want to replace row 3 with itself added to a multiple of another row. So it's going to be, again, subtract row 1. Remember, subtract is the same thing as adding -1 times. So adding -1 times row 1. Row 1 again is going to, and this process is again going to get rid of x because we're going to have an x minus x happening, right, which is going to get a 0x. So our first equation again stays the same. X plus y minus 3z equals 2. So 0x, I'm going to leave a little blank space there. 1/2 y plus 7/2 z equals negative 3/2. And now finally our row 3 is changing. So x minus x, it's row 3 minus row 1. So x minus x is 0x. 2/3 minus 1 is going to be negative 1/3. So negative 1/3 y. And negative 2/3 plus 3, or negative 2/3 minus minus 3, which is the same thing. And I'll just write that as negative 2/3 z plus 3z equals 0 minus 2 is just minus 2. And now let's figure out, okay, well, what's this negative 2/3 plus 3? Well, 3 is the same thing as 9/3, so it's going to be 7/3. 7/3 z. And again, 0x, right? We lost an x term on that bottom. So that's the point. We want to get rid of these variables as we're going through. And by get rid of, I'm just saying we're going to put a 0 coefficient in front of the variable, which simplifies our equations a lot. So now we want to get rid of this y. That's our goal, right? If we get rid of this y, then we can solve for z easily, which this equation would then let us solve for y easily, and then this equation would then let us solve for x easily. So that's our last step, is to get rid of that y right there. Okay, so to do that, like I said, is the variable you want to get rid of. Make sure all the coefficients are 1. So it's a 1 up here. It's not a 1 on either of these two things. So how do I make it a 1? Well, on row 2, I need to multiply by negative 2, right? Because negative 2 times negative 1/2 is 1, positive 1, right? So let's do that. I'm going to write our first equation, x plus y minus 3z, which as always stays the same because I'm not doing any operations to it. Leave a little blank space there, because just so you can see that an x would go here, a 0x would go here, but we don't really write it because it's not really necessary to write, and it gets more confusing. It looks like you're making more progress. You can kind of see the progress you're making if you don't write it. So negative 2 times that, well, it's going to be nothing here. This is going to be y. Negative 1/2 times negative 2 is just going to be 1. And then negative 2 times 7/2. That's just going to be negative 7z equals negative 3/2 times negative 2. Well, that's just going to be 3. Okay. And our final equation stays the same. 1/3 y. There should be a plus here. Hope that's positive. Yeah, just making sure. Just want to make sure that should be a positive plus there. Okay. So then here, yeah, we have the same thing as before. So 7/3 z equals negative 2. Okay. There's our new system. And one more step we got to do before we do the actual type 3 row operation. Row 3 times negative 3. That's what we got to do. Because look, we got to make this coefficient 1. What times negative 1/3 gives me 1? Negative 3 times negative 1/3 gives me 1. So first equation stays the same. X plus y minus 3z equals 2. Second equation stays the same. Y minus 7z equals 3. And finally, our last equation is just getting multiplied by negative 3. So it's going to be y minus 7z equals 6. So just multiply all the coefficients by negative 3 there. Okay, and now we're ready for our type 3 row operation. So I'm going to do, again, our goal is to get rid of this y right there. So to do that, I'm going to take row 3. I want to change row 3, right? I'm going to turn into itself added to a multiple of another row. I can really actually choose either, or no, I can't choose either row. I have to choose row 2 here. The reason is, well, let's try it. Let's see what happens if we do row 1 on the side here as a side note, okay? So I'm going to do that as a quick aside here, right? What happens if we choose row 1 instead? Okay, so let me move this a little bit to the side here. Okay, and I'm going to copy this. So this is not the way to do it. We're not going to choose row 1 as our actual solution, but it's good to understand why we can't choose row 1. So let's say the operation that I'm going to do is row 3 becomes row 3 plus -1 row 1. Let's see what happens. Well, of course, our first 2 equations will stay the same, right? In fact, I can just copy and paste it back again. Our first 2 equations will stay the same. Our third equation is what's changing. So row 3 becomes row 3 plus -1 times row 1. Well, we have 0x minus x, which would give us -x. Y minus y would give us 0y, so plus 0y. -7z plus 3, because minus 3, so it's going to be -4z equals 6 minus 2 is 4. And while we technically did get rid of y here, we reintroduced x into the equation. So we can't do that because there's not this x term, because there is this x term here hanging over the 0x's. We can't use that to get rid of y. Even though it would technically work to get rid of y, it's going to introduce x back into it. But as you can see, when we do it here with row 2, that's why we had to get rid of this x here, right? That's why we had to get rid of this x here. Because then we have another equation where there is no x in it, and that's going to let us do an operation like this, right? That's going to let us do an operation like this right here. So that's our aside, quickly, to see why that didn't work. Let's see what does work. So this is going to be, well, our first 2 equations are going to be the same. So x plus y minus 3z equals 2, y minus 7z equals 3. And finally, our third equation is what's changing. Well, 0x minus 0x, that doesn't change. Y minus y is 0y. Okay, then we're going to have 7. Is this right? Yeah, okay, seems right. Okay, -7z minus -7z. So it's going to be 0z plus 0z equals 6 minus 3, which is 3. Okay, something interesting happened here. Something interesting happened. And this is what's related to the fact that I said at the start that it looked like our system had no solutions. Right? It looked like our system had no solutions. That was my guess, to say that our system had no solutions. This is what happens when we get a system with no solutions. Because, yeah, while we did get rid of y here, we can technically also solve for z, right? What can z be? Right? What equations of z, right? So if I have 0z equals 3, what values of z can I plug in here to make this equation true? There are none. For any value of z, the left-hand side is 0. And this is obviously not a true statement. 0 does not equal 3. So there are no solutions to this final equation. What that tells us is that there are no solutions to the whole system. No solutions. Solutions to the system. And that's what happens. Right? If we did have a solution, I could just solve for z here, back substitute, and get all my values x, y, z. That'd be my unique point, and we'd be golden. But here, we got an equation that's never true. 0 is never equal to 3, and so 0y plus 0z, well, 0x plus 0y plus 0z equals 3 is never true for any values of x, y, z. And so our system has no solutions. So going back up to our question, do the 3 planes have a common point of intersection? The answer is no. And why not? Because when you use your elementary operations to get to simplify and try to solve for a point, you get an equation that's never true, which tells us that there are no solutions to the system. Okay, that's the whole question. Thank you so much for watching. I hope it was helpful, and have a nice day.